Light is an electromagnetic wave, and unlike sound, light can move through a vacuum. The speed of light in a vacuum is 3 times 10 to the 8th meters per second, or 300 million meters per second. Now, as light encounters a different material or medium, it's going to actually move less than that 300 million meters per second. And here's the reason why. As the light encounters a different surface or material, that material is made up of a series of atoms. And so the light is free to move as fast as it can. It's unhindered as it moves through a vacuum. But as it hits this first atom, it is going to, the light is going to move an electron to an excited energy level. It's going to move it to a higher energy level. As that electron moves back down, it re-emits the light to the next atom. Then that atom is going to absorb the light, and it's going to move the electron to a higher energy level. The energy level then goes back down to its lower state and re-emits the light. So these atoms are continually absorbing and re-emitting the light until it leaves that material. And so it's kind of like handing off a baton in a relay. That handoff is going to slow the light down, so it's not able to move as fast as it could if there are no atoms. And we see the denser the material, the slower it's going to move, because there's more atoms in the way if it's a denser material. Now, the ratio of those two speeds, the speed of light in a vacuum divided by the speed of light in that medium, is known as the index of refraction, and it's abbreviated with the letter N. Speed of light is abbreviated with the letter C, and the speed of light in a certain medium is abbreviated with the letter V. So speed of light in a vacuum is letter C, but speed of light in a certain material is the letter V. And we see that the slower, it's inversely related to the index of refraction. So the slower this light moves, the higher the index of refraction. So the denser the material, the higher the index of refraction. Now, as light hits a certain surface, some of the light is going to be reflected. And the reflected light is going to be reflected at an angle equal to the incoming light. We call the incoming light the incident ray. And we measure all angles with a normal line. That's a line perpendicular to the surface. So the reflected ray is going to be at an angle equal to the incident ray. However, depending on the type of material, some of the material goes through, or some of the light goes through the material. It's transmitted through the material. And so we refer to that as the refracted ray, because that light is bent as it goes through the material. Now we show this relationship of the index of refraction to its angle through something called Snell's law, or the law of refraction. So this determines how much the light is bent, and it states that the index of refraction of the first material times the sine of the angle of the first material, or the incident angle, is equal to the index of refraction of the second material times the sine of the angle of the second material, or the refracted angle. So why is this light bent? The reason that the light is bent is because let's give an analogy. Let's say that a barrel is coming at an angle from the road made out of macadam. So this would be an analogy of a small index of refraction. It's able to move pretty fast on the macadam to the grass. And so this would be like an index of refraction that's a higher amount, like glass, because it's going to be slow the barrel down. And so as the barrel gets to this break of the road and this boundary, what's going to happen is that the leading edge of the barrel hits the grass first. And that is going to then twist the barrel and make it move at a slightly different angle with respect to the normal line. It's going to be at a smaller angle. We've seen this before. If ever you had a straw in a glass of water, you would see that the straw actually looks bent. And it's always going to look bent towards the normal line. Because as we go from a smaller index of refraction, for air we approximate the index of refraction to be about 1, to water, which we have an index of refraction of about 1.33. So as it gets more dense, the index of refraction goes up. And as the index of refraction goes up, it's going to make the light bend towards the normal line. Another application of this is, let's say that you're trying to get a fish out of some kind of a fish pool. And so you're looking at the fish, but the light that's bouncing off the fish is actually going to do the opposite. The light bouncing off the fish goes from a higher index of refraction with water to a lower index of refraction with air. So the light's coming this way. And so it's going to bend away from the normal line. But to us, to the observer over here, looking at the fish, it looks like the fish is a little bit higher according to our angle. And so we try and aim at a certain spot, but the fish is always lower than where we aim. That's because the light is bending. Now, an example problem of this, let's say we have light traveling in the air, it strikes a flat piece of uniformly thick glass at an incident angle of 60 degrees. So we have light coming in, here's the air, and the light's coming in at an angle of 60 degrees, so a pretty steep angle. And when it strikes the glass, we say that the glass has an index of refraction of about 1.5. Now, it all depends on what type of glass that you have, whether it be crown glass or whether it be Pyrex. They'll have different values. That's about 1.5. So in this case, it was given to us. Air is 1. Because it has a higher index of refraction, the light's going to be bent towards that normal line. So we expect an answer somewhere less than 60 degrees for this angle. So Snell's law says index of refraction times the sine of the angle in the air is equal to the index of refraction times the sine of the angle in the glass. So we replace these with our values. We have 1 times the sine of 60 is equal to 1.5 times the sine of our unknown. And we get our unknown angle, comes out to be 35.3 degrees, which is less than 60, which is what we expected. Because it's a denser material, it has a higher index of refraction. It's going to bend towards the normal line. Now, we had said that if it goes from a high to low index of refraction, it's going to bend away from the normal line now. So let's say that we're going from diamond, which has a high index of refraction, to air, which has a low index of refraction. So as the light travels in, it's going to bend away from the normal line. And so at some critical angle, as we increase the angle of incidence, it's going to increase the angle of refraction. And at some critical angle, what's going to happen is that this is going to bend so much that it just skims the surface. Any angle greater than this, what we refer to as critical angle, is going to make the light completely reflect or bounce off. See, some of the light's reflecting, some of it's refracting. And so if we get to this critical angle, none of the light is transmitted into the other material, into the air in this case. This is what diamond cutters do. They want all of the light, to exit here towards our eyes, and so kind of get that sparkle effect. And so they cut it in such a way that it's total internal reflection. That's what we refer to this as the light does not come out. It is all reflected. So we say that it is total, internal, none of it goes through to the other material. Reflection, it's all reflected. So we get that sparkle effect because all the light's coming out towards our eye. So total internal reflection says that for some given critical angle, all of the light is going to be completely reflected. The angle of refraction is 90 degrees in that case. Any angle of incidence less than that, some of the light is reflected and some is refracted. Any angle of incidence greater than that critical angle, and all the light is reflected back into the material. And so we replace in Snell's law, we replace the second angle with 90 degrees at that critical angle. And the sine of 90 is 1. So this value here is 1. And so if we rearrange, the sine of the critical angle is the ratio of the index of refraction of the second material divided by the first. But notice that this is only true if material 1 is more dense, meaning that the index of refraction of material 1 is greater than material 2. Mathematically, we see that if the index of refraction of material 1 is greater than 2, it is going to be less than 1. If the index of refraction of material 1 is less than material 2, then it's going to be more than 1. You cannot have a sine function have a value more than 1. The maximum value for the sine of any angle is 1. So mathematically, n2 has to be less than n1. In other words, material 1 must be more dense than material 2 for this total internal reflection to occur. So again, as light hits a different material, some of it's reflected, but in certain materials where it's transparent, some of it will go through. As it goes through, if the second material is more dense, it'll bend towards the normal line. If the second material is less dense, it'll bend away from the normal line. And if we go from a high to a low index of refraction, we get a certain angle where none of it is refracted into the second material. In other words, all of it's reflected. We refer to that as total internal reflection.